Okay, now we learn the concept of thermal resistance. Now we learn the concept of thermal resistance. This idea is derived from the idea of electrical resistance. You are all confident about electrical resistance. You learned your 12th class about electrical resistance. So very quickly, let's revise electrical resistance. If you have a resistance of R ohms and the potential difference or the voltage applied across that resistance is V and the current passing through it is I, then what is the Ohm's law? V equal to IR. The Ohm's law tells you that V is equal to IR. So what is the expression for I? I is equal to VR. Now in electricity, you know what is meant by current. Current is the quantity that flows. I is the quantity that flows through the resistor. V causes the current to flow. What is the role of potential difference? The potential difference that drives the current flow. If there is no potential difference, there will not be any flow of current. So the driving force here is the potential difference. And what is R? That is the resistance to current. You know, resistance is some opposition. So there is some opposition to the flow of current. Higher that resistance, lower will be the current. So the potential difference tries to push as much current as possible, but the resistance opposes it. Then there is a particular amount of current that decides or that's depending on V and R. Is that clear? Now we are going to see a very similar analogy. We are going to see the resistance, the electrical analogy. This should be first revised. You should know the electrical resistance, ideas about electrical resistance, what flows, what drives the current flow, what opposes the current flow. Similarly, if you have a plane wall, you just derive the expression for a plane wall. What is driving the heat transfer? The temperature difference. This is at a higher temperature and that is at a lower temperature. So the potential difference, instead of potential difference, we have what? Temperature difference. Now what does the temperature difference drive? It drives the heat transfer. Because of this temperature difference, there is a flow of heat transfer. So what flows?
Heat transfer.
Flows.
The
heat flows. And what is opposing the heat flow is the resistance. The material has a thermal resistance. There you have an electrical resistance. That is the resistance to current. Now this material has a resistance to flow of heat. For example, you have a plastic, then it opposes the flow of heat. If you have an insulator, it opposes, reduces the resistance. So here you have the thermal resistance, which is called RTH. That's the nature of the material of the wall. If the material is a good conductor, for example, it's a metal or a very good conductor, then the thermal resistance will be low. If it is an insulator, like plastic or wood, then the thermal resistance will be high because it doesn't allow heat to flow easily. Like how you have the Ohm's law, here you have the law for the electrical analogy for temperature, thermal resistance. Instead of I, what do you put? Q. Instead of potential difference, what do you put? Delta T divided by R. Here. So Q equal to delta T by R. This is the equation, it's a very important equation for thermal resistance. You use this formula to solve problems easily. Instead of going to the basic differential equation of heat conduction every time to solve problems, we are going to use this formula effectively and solve problems on where walls are in series or walls are in parallel or you have a combination of series and parallel walls. We are going to make use of thermal resistance concept. So the first idea is something we have to analogous, you have to find analogous quantity. Here current flows through the circuit, similarly heat flows through the wall. Here the potential difference drives the flow of current, temperature difference drives the flow of heat. The electrical resistance opposes the flow of electric current. The thermal resistance gives an opposition to the flow of heat. So like the Ohm's law, We write a law for the thermal resistance, which relates Q delta T and R thermal, very similar to the relation between I, V and R. Now what we are going to do is, we are going to derive the thermal resistance for a plane wall. It's not very difficult. We are going to derive the thermal resistance for a plane wall. Without any internal heat generation, of course at steady state. The idea is, we are going to write the equation we have derived earlier in this form, and then we are going to see what is in the location of R thermal. So for a plane wall, steady state, one dimensional, no heat generation, we just derived the heat transfer rate. We derived that the heat transfer rate was given by K A T1 minus T2 divided by L. Just now we derived the thermal resistance, the heat transfer through a plane wall. I'll call this as just Q. Now what is this T1 minus T2? That is delta T. So this is already of that form. Now I am going to put it exactly of that form.
Minus
Q equal to, T1 minus T2 divided by, I am going to pull Ka down because it's not there here. You have only delta T in the numerator. All the other things you bring it to the denominator. So what will this happen? L by K. Now it is of the form delta T by L by
K.
So what is L by K? That has to be the thermal resistance. Because you have put it on the form Q equal to delta T by R thermal. Everything below is going to be the R thermal. So R thermal for a plane wall is L by K. Very important. If L is large, resistance will be large. If you have a thick wall, then heat cannot flow easily. If K is small, resistance is large. Or if K is large, resistance is small. For a metal, conductivity will be large. Thermal conductivity is large. So resistance will be small. For an insulator, thermal conductivity will be very small. So the resistance will be large. And then higher the area, lower will be the resistance. If it's a high area, it can easily conduct. It's a small area, then the resistance will be large. So these are the parameters that affect the thermal resistivity, thermal resistance for a plane wall. This expression is there in the data book. This expression you can find in the data book. Is that clear?